All right. So, some things you'll be told in this is, note. Um, so, the derivative is the slope of the tangent line. Okay. Yep. You'll be given that. And then, it begs the question, though, okay, so the derivative is the slope of the tangent. I know what slope means. I know what line means. But tangent line. Okay? And if I ask you what the tangent line is, you'll say things like, oh, it touches the curve in exactly one place. I don't think so. I don't think that's quite right. Now, let me show you why I don't think that's quite right. So let's use f of x equals sine of x. Okay, so I have that. And, I'm going to go with a point, maybe, 1 should work just fine. So if I look at 1, so what I'm going to do is say my slope is equal to f prime at 1. Okay, so that's the slope. And then I'll make my tangent line. I'm not going to do a y equals or anything like that. I'll just do the slope in the function. So I'll take f of 1 plus m that I calculated up there times x minus 1. And there you see at 1, this is the tangent line. I zoom in. Yeah, I think everybody would agree that's the tangent line. But oh, look there. It touched the curve in another place. So that's crap. To say, oh, the tangent line is a line that touches the function or touches the curve of the function or the graph of the function, in only one place. Right there. Crap. Not true. Okay, so what the heck is the tangent line? Okay, this is what I want you to commit to your heart, is the tangent line is the best straight line. Well, of course, most lines are straight, I suppose, but it is the best straight line approximation to a function at a particular point. That is what a tangent line is, and we can look at that here. So here's the tangent line at this point. Now let's just start zooming in. And this is what we mean by best straight line approximation. I'm going to center it a little, try to center it a little more. Okay, and so we're hovering right over that, trying to keep that point pretty much in the center here. So I'll just keep going in, and what we notice is happening, right, is where we used to have two lines, a black line and a blue line, I'm only seeing the blue line. What happened to the black line? Well, it's underneath the blue line. There it is. They look the same. This line, which is a straight line, the blue one, and this curve, f of x equals sine x, right here at 1. Now, notice we aren't very far away here, right? We're at 0.9997. Okay, so it's a really good straight line approximation, but not for very long. Okay, so we can come back out here. and we see that, here's one. Well, I'm only at 0.7 this way, and already they're pretty far apart, right? So it's not a great straight line approximation for very long, but at that point, that was a darn good straight line approximation. It is the best straight line approximation for that function at a point. And what we know is at that point, they're equal, they intersect, and then close to the point, they're nearly indistinguishable. And so, that's, something very interesting about a tangent line, but also very useful. And so, for instance, now let me change this to 0 and 0 and 0. And there we have that tangent line at 0. And that's actually, if you look at it, you see it's just the y equal x line. And so it turns out for really, really small angles, now how small? Now remember, sine of x is in radians. For small angles, these are pretty much indistinguishable. So here I'm at an angle of 0.15 radians, and they look, they look pretty much the same. Now, how big is 0.15 radians? Well, 0.15 radians, and then to get to degrees, well, multiply by 180. This is just the unit change, divided by pi, because there are 180 degrees in pi radians. So I've got radians over radians. Radians cancel. I get degrees. And so at 0.15 radians, I'm at about 8.6 degrees. That's actually pretty big when you think about it. And how are we doing out here at 0.2? They are still very close. I mean, if we look at the relative size difference, there's not much difference there. We could look at, for instance, at 0.2, we could ask, well, how big is, and it looks like the blue one's on top, so that's y equal x. So I could ask, what's x minus sine x look like? And I could actually give it a name. So let's call it error. Well, error of x. And as you look at this, it's not very big, so I can actually ask, well, okay, how big is the error? So e of 0.2, 0.0013 difference between those two curves. And so, well, how many degrees is 0.2 radians? We're clear up to 11 degrees. And, now as I move over, it starts to get bigger. But remember, sine of x and x are much bigger. And so we could also ask relative error. And so we could take this whole thing and divide by sine of x. And we look at this relative error, and we see that, here's 0.05, so that's a 5% error. So here's 1% error. Well, it looks like at about, we hit 1% error at about 0.25, and maybe that's as much error as I would ever want. Who knows? 1%. But see, we're almost to 15 degrees. So really a very good approximation. Okay, so what good has that done? Well, think about being able to approximate with that straight line. All of a sudden, instead of asking, something like, when is, and actually, as we just saw in another video, that this will probably solve this just fine. But But let's try sine. I'm going to square it. So sine squared of maybe 3x plus 2 is equal to I don't know, 0.5, say. Wow, and it solved it. So that's nice. I mean, we got lots of different answers here, and we got this one. So honestly, it's sort of a problem on my part as a teacher to really try to instill in you why it would be nice. But if I could use the function x instead of sine x, what I would be trying to solve here is 3x plus 2 quantity squared. Whoops. I don't know what just happened there, but oh, I hit the up arrow instead of the caret. So squared is equal to 0.5, and it solved that one just fine as well. Now it is actually a little interesting that did it find two answers? Yeah. So here it found these negative answers. Okay, so oh well, probably I needed to use well, maybe not a negative on that. But so it found these two answers, and it could be those are the answers I'm interested in, because remember that I want sine squared here on this, and it's pretty close, right? But I can solve this one, and that's kind of the point I'm getting at, is I can actually solve this problem because I know the quadratic formula. So even with that square in there, I could say, well, the sine function itself is just the same as the identity or x, and so then I could put this 3x plus 2 into that, which just makes it 3x plus 2, and then set that equal to 0.5, and what if I made it just 0.1? Well, might need to change that one as well. Look how close those are. So again, you see if those are right on. So again, if that angle is pretty small, which it would need to be to keep the sine a smaller number, this approximation here, way better than that one. And once again, it's a bit difficult to truly point out how important this can be to do these approximations, but it can be extremely important to be able to do this, because we can get nice symbolic answers and so forth. So here, like I say, I can get an answer to this one, and that answer is right on a couple of the answers for the sine function here. On the other hand, I can't do this one so well because doing the inverse sine function, I don't know what the heck that is. Now I can look it up in a table, which is kind of what Desmos is doing. But this is a extremely wonderful thing to be able to do, is do this approximation, and hopefully over the course of the semester we can build that appreciation in there. But like I say, it can be tough with technology to really decide that this was a big deal going from this line here to this line here. But it is a very big deal, and a very nice thing that calculus and derivatives and so forth does for us. So there's another sort of reason of why calculus, and also just this idea of, what is a tangent line? This one, that's what we want you to know. The tangent line is the best straight line approximation to a function at a particular point. Okay, biggie there. I'm sure I'll try to get that, on quizzes or exams or something, because, if you can remember that, I think that's a very, very good way to understand what this whole tangent line thing is doing for us. Okie doke. Well, I've waxed on plenty long, and so we'll finish here.